looked at related rates, which was basically applying our derivative to like kind of application type problems. Now we're going to look at two other types of applications that we can use with our derivative. The first is what we're going to call, it has a couple different names. One is the tangent line approximation or linear approximation. Sometimes you'll also see it written as linearization, okay? But basically all of those mean is to use the tangent line to approximate other stuff. So I think it's helpful to kind of look at a graph. Alright, so I have a graph. Yes? Okay, what are the two things that I need in order to write the equation of the tangent line? A point and a slope. Alright, okay with that. So let's say that we label this point at A, f of A. That's way too far above. There we go. So what would the equation of that line then be? How do we write out the equation of a line? Yeah.
Point slope function.
Yeah. Okay, so we have y minus, what's our y value? F of A. Okay. Equals. It would be the slope. Okay, how do we find the slope of the tangent line?
Derivative.
The derivative. So we would have f prime of A. Yes? Times x minus A. Yes, no baby. Okay. Now, for our purposes, usually we go ahead and leave it like that. But this time, we are going to go ahead and solve for y. I would add f of A to both sides. Yes, no baby. Again, same equation that we've used all up until this point, except now we just have it labeled as f of A, f prime of A, for our y and slope. Okay. Now, what we can do is, so pretend with me for a second. Like, I know this is a quadratic, but like, right, there are lots of functions out there. There are some functions that are like really, really complicated to plug into, meaning that to actually evaluate a number at it, it's really hard to get an exact answer. Or sometimes we don't know enough information about it to get an exact answer. But if I have this linear line, so let's say we had some point value, and that's my point. Okay, so that's B. So B is on my tangent line. Yes or maybe? But would we agree that this B value, right, whatever that y value is, would be a fairly good approximation for what my function value would be on my blue graph? Are they relatively close? Yeah. So what we can do is we say that this is our linear approximation, so L of x. And then what we can do is we can then plug in B. We're going to plug in B to our L and get some sort of value. And that is going to approximate for us whatever f of B would have been. So we are using the tangent line. To approximate the value of a function to a given value. So in this case, my given value was A. Okay? My number close to that value was B. So notice that, like, if say I had picked some value, I don't know, way over here instead, C, right? Would this point be a very good approximation for my blue curve? Not really. So that's why I say close to, because the further away you get from your original value, the worse your approximation is going to be. So we need it to be relatively close to whatever the given value is. Like, we wouldn't want to be given 2 and we're trying to approximate 10. That would be a really bad approximation. But we could be given information about 2 and we're trying to approximate 2.2 or 1.9. Okay. Questions so far? Alright, let's look at an example then. Alright, so it says find the tangent line approximation of the following function at the point 0, 1, where f of x equals 1 plus sine of x, and we are then going to use that, that's not right number. So then approximate f of 0.1. So what type of function do we have here? It's a trig function. Okay. If I were to plug in 0.1 for sine, is that going to be a nice pretty number?
No.
No, because 0.1 is not a angle, right? It's not like a common angle. So we're not going to get a nice pretty number there. So this is a good instance where it's helpful to approximate it. So what did we say are the two things that we need for a line?
Point and slope.
Point and slope. Do I have a point?
Yeah.
Yeah. Do we have a slope?
Yeah.
Do we? It's already given?
No.
No. Can I find the slope?
Yeah.
Yes. Find the slope we can. So how do I find the slope?
Take the derivative.
Alright. So what is the derivative of 1 plus sine of x? Just cosine x. And again, we're specifically wanting the derivative at our a value. And in this case, our a value is whatever is given to us. So at this time, it is 0. So what is cosine of 0?
1.
1. Okay with that. So then I'm still just building my equation the same way that I would before. My y value is also 1. My slope is 1 times x minus 0. But again, remember that we are going to solve for y, and we're not going to leave it as y because again, this is a linear approximation, so we're going to represent that as L of x. So if I distribute my 1, I still just have an x. If I add 1, I would get x plus 1. Yes, no, maybe so. Are we all okay with that? So that would be, if they just said find a linear approximation, that would be a linear approximation. Then we actually want to use that equation to approximate f of 0.1. So in that case, we are just plugging in 0.1 into our approximation, and what do we get?
1.1.
1.1. And so that would be my answer. Are we all okay with that? Now, lucky for us, we can find the exact value for this function. There are some out there that it would be really difficult to find the exact value for, but if we wanted to, we could plug this into our calculator. So if we plugged in 0.1 in for f of x, what do we get? Someone typey for me. Make sure you are in radians. 1.01?
1.00998.
Yeah, it should be 1.0998, right? But what does 1.0998 round to? 1.1, right? So our approximation was fairly close, yes? Now, if I then instead plugged in, like, say, 2, okay, would I have gotten as close of an approximation?
No.
No, it would actually not have been a very good approximation, because remember your sine graph was like this, right? So depending on if you're on the downtrend over here and you're trying to use this one, it's not going to work out very well. So, is this an overestimate or an underestimate?
Slight underestimate.
Slight overestimate. So it is an over. Okay. Now, but what, again, the whole purpose of this is that I don't want to have to plug in to find the exact value. Agreed? Like, I'm using this as an approximation, just kind of like we did on our bell work. Like, the goal is to use that to approximate. So I want to be able to know if it is an over approximation or an under approximation without having to actually find the value. So how might we do that? What do we think? Do we think that they will always be an overestimate? Okay. Well, let's look at the one that I have on the previous page, right? Would this tangent line, so my b value over here, would that have been an overestimate or an underestimate?
Overestimate. No.
So this value would be my L of b, right? This value would have been my f of b. So it would be a what? An underestimate, yes? Because my line is under my graph, so my y values are going to be under what the actual y values would be. Agreed? Okay. So what's different about this graph versus, okay, like let's look at what maybe this function looks like, yes? Okay, what does our graph of sine of x look like?
Curvy line.
Okay. Well, let's try and get a little bit more specific than that. Okay, specifically close to 0, right? At the point 0, 1, what would be happening?
It's like crossing down.
So usually sine of x is crossing the origin because its sine is 0 at 0. Agreed. And it's actually going up, not down. But what else has happened in our original function?
There's a plus 1.
There's a plus 1. So that means that everything has been shifted up 1, right? So it is still going to be increasing, right? And then somewhere over here, and then down here it's decreasing, and so forth. Yes?
Yeah.
Are we okay with that? So now, my slope of the tangent line. So my tangent line is at approximately, 0.1, so it's slightly over here. Yes? Which is why we get an overestimate, yes? Slightly, but still an overestimate. So what is different about my graph here at point 1 versus the graph that we had here?
That one's concave up.
This one's concave up, and this one is
Concave down.
concave down. Okay. So what do we think that means?
Concave up is underestimates. Concave down is overestimates.
Always?
No.
Both of those are doing what?
Increasing.
So this one's increasing and concave. What's wrong with? This one was also increasing, right? So might it be a good idea to at least check what would happen if we were decreasing on them? Yeah, just to make sure that it is just dependent upon our concavity. Yeah?
Yeah.
So let's look. So we looked at both of the increasing. underestimate. Here we're concave down and increasing. We said that was an overestimate. Yes? Now let's look at, so if I'm concave down and I am decreasing, is that still an overestimate?
Yeah.
Yeah. And if I'm concave up and decreasing, is that still an underestimate?
Yeah.
Yes. So it is just based upon concavity. So if we are concave down, we're going to be an overestimate. If we are concave up, we're going to be an underestimate. And if it helps, go to that down and over, both have an O, and up and under, both have U. Yes, no, maybe? Which means that in all reality we really just have to be given the concavity, yes, of a function, and then we would know if my linear approximation was an over and underestimate, yes? What's the other thing that I could be given instead of the concavity to be able to find the concavity?
The derivative.
Not the derivative, but the
Equation.
second derivative, right? I would either have to be given enough information, if I'm given the original function, yes, but we're not always given the original function. We're not always even necessarily always given the derivative function. But if they told us f prime or f double prime is positive, what does that tell us?
Concavity.
It's concave up, right? And so then we know we have an underestimate. So they can just sometimes give us information about our second derivative instead. Alright. Questions with that? So that was given a function. We can also do this given a table. Again, we have to become friends with the table. Become one with the table, right? Our table questions are really, really easy, okay? They should be give me points, okay? Basically, they give you all the information that you need. So this one says selected values of the derivative of the function g are given in the table. It is also known that g of 4 is 12. What is the approximation for g of 4.2 found using the line tangent to the graph of g at x equals 4? So again, what are the two things that we need to write the equation of a line?
Point slope.
Okay, do I have a point? Yeah, g of 4 is 12, and they specifically tell us that we're wanting our linear approximation to be at 4. So we get y minus 12 equals x minus 4. What goes here? The slope, okay. What is the slope of the tangent line? Where did we get that from?
This is g prime of x is 2.04.
Yeah, so our slope is also the derivative at that point. We're looking at the point of 4. So I just go to my table, go to 4, and my slope is 2.2. We don't have to do a lot of work with these types. If it's a table, it's just do you have an understanding of what it means to be a derivative and what it means to be a linear approximation? We don't even have to take the derivative. We just have to know what a derivative means. So again, we're going to go ahead and solve and rewrite this as L of x because it's our linear approximation. I am going to leave this in factor form. Because remember that my whole goal is that my x value that I plug in here is going to be very, very close to the original a value, yes? So this subtraction should be pretty easy to do. So that's why if we leave it in that factored form, then we don't have a whole lot of multiplication and stuff we have to do. We can just do that subtraction first. It'll work if you multiply out. I just think it's usually a little bit easier. So then what are we approximating? 4.2. So we're just going to plug in 4.2. So what is 4.2 minus 4?
0.22.
0.2. What is 2.2 times 0.2? Ideas?
0.6. No.
So 0.2 is going to be
0.44.
yes. But it's like a smaller decimal, yeah? So it would be like a fraction, yes? And it's in the 10th spot, yes?
Mm-hmm.
So it's going to move our decimal over 1 for our original number. And then you can just do your 2 times your 2 is going to be 0.44, so we get 0.44. Yes, so maybe do you remember that that's how fractions and decimals work? We remind ourselves about it a little bit. Again, if you left it like that, you would still get the full credit. But we do, like with the multiple choice question, you do need to be able to like do a little bit of mental math. But plus 12, we end up with 12.4. And now we are. Yeah, I know that. Yeah, just sign up, please. Right. Questions on there? Okay, ready to look at L'Hopital? L'Hopital. He was a French mathematician. And the rules named after him. So we're going to be looking at limits, which is why I said like this kind of section is kind of a nice review from first semester, because we got derivatives, which is basically all of first semester, but we also have limits, which was that thing that we did at the very, very beginning of the year. Yes? Alright. So, what is an indeterminate form? Or a limit. Yeah.
A form where the limit doesn't exist. But the limit can be found.
Okay. I agree more with the second one. Yes. What are some specific examples of that?
Asymptotes.
So that would be where it's undefined. Indeterminate form does not mean that it is undefined.
Oh, holes? No.
Holes would be another example of where it would be in an indeterminate form, and then I can evaluate it. Yes. Yeah.
Isn't it when like the numerator and denominator go zero?
Yeah. So one example would be is if I have 0 over 0. So it's not that I can't find it at all, it's that I can't find it yet. Remember, so when we get 0 over 0, or the other one, which we don't get quite as often, but is still an indeterminate form, is infinity over infinity. And so what that tells us, or should trigger for us, is that, oh, it's not that I can't find it, it's that I can't find it yet. I need to do something else to it, because I have stuff on top and bottom that are the same. Now, if I get a 1 over infinity, like a number over infinity, remember that that means that then, or 1 over 0, that's where we either have undefined because it's positive or negative infinity, or if it's 1 over infinity, it goes to 0 instead. But we are specifically looking at indeterminate forms, which is 0 over 0 or infinity over infinity. So up until now, what are some of the other methods that once we got that we could do to make it not an indeterminate form?
Factoring.
Factoring. So to factor and reduce to something, right? I get 0 over 0 because they both have a common factor. I reduce that out. Now it's no longer 0. Now we can find our limit. What else? This was the one that y'all didn't like all that much. Remember that we can find and multiply by the conjugate. Yes? Yeah, our stuff with square roots. And then lastly, the other one was our special trig limits. But again, these are very specific cases, right? Because what happens if I have something that I can't factor? It doesn't have a square root in it, and is not a special trig limit, yeah? But I still got 0 over 0. So like I know that there technically should be a limit for this, because it's an indeterminate form. So there should be something that potentially reduces out. I just don't know how to do it, because it doesn't meet one of these three things. And so that's where L'Hopital's rule comes into play. So L'Hopital's rule tells us that if I have this limit, and the limit is an indeterminate form, substitution, okay, we will take the derivative of the top and the derivative of the bottom. Now, it is important to note, this is not the quotient rule. So look, I'm not applying my quotient rule. I'm just taking the derivative of the top and the derivative of the bottom. However, that also means do not try to apply this when we're doing something that requires the quotient rule, okay? So this is for limits, not for taking the derivative. Here I am just taking a limit. But it is going to be important that we check that it's in determinate form first, because this won't work if it's not in indeterminate form first. Alright, you ready for a new table? These are kind of fun. Alright. So I have the limit as x goes to 0 of e to the 2x minus 1 divided by x. So what do we always want to try first? Direct substitution. We're trying to plug the thing in. Yes? We're okay with that? Okay. Now, let's note, just by visually looking at it, if I plug in 0, what is e to the 0? 1. What is 1 minus 1? 0. If I plug in 0 for x, what do I also get? 0. Okay? Now, we are going to have to verify that this is an indeterminate form. And I'm going to do that separately. So I'm going to take the limit of the top and the limit of the bottom. Yes, no, maybe. Because we can't say that this equals 0 over 0 because equals implies that it equals that. An indeterminate form implies that it can't be determined. So we don't want to put that it equals 0 over 0, but we do want to indicate that I do know that these two limits separately do equal 0 over 0. Are we all with me there? Okay. So then what we can do, again, is we can take, here, I'll go ahead and move right, the derivative of the top. Okay. So I tend to write an LH for L'Hopital's over the equal sign, just to indicate to myself and the reader that I'm applying L'Hopital's rule. It's not required, but again, you are taking the derivative of the top and the bottom, so if you start having stuff just like magically go away, sometimes it can be a little like suspicious, but if I put LH, it's understood that I'm applying L'Hopital's. I have not evaluated my limit yet, so my limit sign still carries. But then we have to decide what is the derivative of e to the 2x. Yeah, I have to apply a chain rule, right? Because e to the stuff, the derivative of that is still just e to stuff. But I don't just have an x in there. I have a 2x, so I do have to multiply by the derivative of the inside stuff. So the derivative of 2x is 2. What's the derivative of a negative 1? 0. Okay? Then on the bottom, remember, I'm not using a quotient rule. I'm just taking these limits separately. What is the limit of x? 1. Oh, that's nice. Because now can I plug in? So what is e to the 0 again?
1.
1, right? And then 1 times 2 gives us 2 divided by 1 is 2. So my limit here is 2. Questions on that? Alright, let's think about our next one. What are we going to this time? Infinity. Okay. Can I actually like plug in infinity to stuff? Not really, but I can kind of think about what would be happening with that. So if I were able to plug in infinity to an x, what am I going to get? Infinity, right? It's going to get infinitely big. So the bottom is infinity, which is good. However, if the top happens to be not infinity, then we're going to get something else. So we also need to check what the top is. What is the limit as x goes to infinity of just the natural log of x? If we don't recall, remember we can always go back to our graph. What does the graph of the natural log of x look like?
It's like a curvy line off of the y-axis.
Cool, like that?
Yeah.
So as my x is getting larger, what is happening to our y values?
Larger.
They're also getting larger. So do we agree that the limit as x goes to infinity of the natural log of x equals infinity, as does our limit as x goes to infinity of x? Yeah? So if I have infinity over infinity, what is that? An indeterminate form. So, I have the limit as x goes to infinity of the natural log of x divided by x. I'm going to apply L'Hopital's rule. What is the derivative of the natural log of x?
1 over x.
1 over x. What is the derivative of x?
1.
1. Okay. Now again, can't plug in, but we can think about this. If I plug in infinity onto the bottom, what's going to happen?
Versus 0. It's going to get smaller.
The whole thing would get smaller, right? My denominator is going to get bigger and bigger and bigger, which makes the whole fraction smaller and smaller and smaller. Specifically smaller towards 0. Questions? Yes. We got what we did. So then my limit for this one would be 0. Yes, no, maybe. What questions do we have there? Alright. This last one. We'll wait until tomorrow to finish that one up. So this is also using L'Hopital's, but it's just L'Hopital's from a table. But we will have to remind ourselves about some chain rule stuff, which is a good reminder. Some of us struggled with our chain rule stuff from tables and function notation. So again, kind of good refresher from last semester. So that's where we'll start off tomorrow.